Hi, I'm going to present the paper about decoupling cores, kernels, and operating systems. This paper presents the Barrelfish DC, an extension to the Barrelfish OS, which decouples physical cores from native OS kernel, and furthermore, the kernel itself from the rest of the OS and application states. In Barrelfish DC, native kernel code on any core can be quickly replaced. Kernel states move between cores, and cores added and removed from the systems transparently to applications and OS process, which continue to execute. Before going to present about whole parts of the paper, I would like to give a short outline about this paper, about this presentation. First, I will introduce about the motivation in trends in hardware and software. And then I will present about the implementation on booting and shutting down cores dynamically. The rest of the paper, which about evaluation and conclusion, will be given by my partner. So first, what's happening to hardware? Today we are mostly constrained by power consumption. This will bring us, for example, reconfigurable cores, which means we can dynamically change behavior. So this is we already do today, like DVFS, which stands for dynamic voltage and frequency scaling, and turbo boost and SMT. Also, there's some research technique, such like core confusion, which allow us to fill cores multiple physical cores into simple, more powerful cores or speed them up again. On the other hand, the future may have to do dark silicon, which means we can have many cores, but we cannot power them all at the same time. So what that mean for us? For adding and removing cores in the system? Well, we already do it today. For example, if course fails or if reallocate course to different machines. On the other hand, you may take cores out of service because we will not power them all at the same time. Also, there's heterogeneous cores in our machine, giving us asymmetric performance. And for example, one such logical conclusion of this would be conservation cores. Now we imagine that we build an OS in a dark silicon area. So you have set a heterogeneous cores and you need to switch between the cores based on your workload. But you also need to power down and take cores out of service because you don't have the power to power everything at the same time. So this is the current model today. The kernel running as a single program in all cores, and every cores run the same code, as it's hard to adapt like heterogeneous cores. So what happens if you move a core in such a system? Well, we have to go deep to the data structure to reflect this change. Typically, this requires global coordination, and also at the data structure may be global share protect by locks. What happens if processor holding on the locks? So this is a lot of issues there. So what's happening to software? In software, we usually need to adapt to different work in our OS. Now, general purpose kernels were very useful to adapt, but we still have to adapt to modify build, boot, and runtime. For example, to facilitate debugging with profiling and tracing. And sometimes application requirements are very strict, such as real-time support, and it's hard to adapt everything into general purpose kernel. Now, there are also research techniques that works by modifying or upgrading cores on the fly, as is the case, for example, K-supplies in Linux or K42 update mechanism. So we argue that a good architecture model dealing with dynamic cores or adapting to heterogeneous cores on or changing software requirements is a multi-kernel model. In multi-kernel, uh, each core runs separate kernel program, and state is currently in per-core states into what we call OS node. Now, we have to run applications on top of that, and applications may share state between cores. Therefore, we replicate states between cores using asymmetric message passing. So, however, a multi-kernel model is not enough dealing with dynamic cores, so we still need to deal with OS node. So, therefore, we use a basis which Barrelfish DC or Barrelfish OS is an implementation of multi-kernel, and we add some features to Barrelfish DC, which I mentioned at the beginning. Treat cores as much as possible as plug device. So we'll next love how we're booting a core dynamically with boot drivers and how we shut down a core in system. We use a technique that externalize kernel states that allow us to decouple cores, kernels, and operating systems. So, and we should mention before that in this paper, they only focus entirely on mechanism, and so do not address scheduling and the policies for kernel replacement, kernel power management, or application migration. Note also that the paper's main motivation in Barrelfish DC is adapting the OS for performance and flexibility. And so this paper doesn't consider about fault tolerance and isolation. So the first is booting a new core. Bring a core online is a question of turning on, updating this table, and creating per core states when needed. Previous version of Barrelfish also adapted this approach and booted all cores during system initialization, though there has been experimental work on dynamic booting of heterogeneous cores. Barrelfish DC targets a broader hardware landscape with complex machine comprising potentially heterogeneous cores. Since Barrelfish DC runs a different kernel instance on each core, there's no reason why the same kernel code should run everywhere. So we need an OS representation of a core on machine, which abstracts the hardware-dependent mechanism for bringing the core up and down. Therefore, Barrelfish DC introduced the concept of a boot driver, which is the piece of code running on the home core, which manage a target core and encapsulates the hardware functionally to boot, suspend, resume, and power down later. Currently, boot drivers run as processes but closely resemble device driver and could equally run as software objects within another process. And these are the 5 steps. A new core is brought online as follows. First, the core is detached by some platform-specific mechanisms and its appearance registered with the device management subsystem. And then Barrelfish DC select and start appropriate boot driver for the new core. The third step is Barrelfish DC select a kernel binary and an argument for the new core and direct the boot driver to boot the kernel on the core. The next step is the boot driver loads and relocates the kernel and executes the hardware protocol to start a new core. The last step is the new kernel initialize and use existing Barrelfish protocol for integrating into running OS. Booting a core in Barrelfish DC only involves 2 processes, the boot driver on home core and the kernel on the target core. For this reason, we require no global locks or other synchronization in the system, and the performance of these operations is not impacted by the load on other cores. Shutting down a core. Shutting down a core is much harder than booting because we need to deal with per core state. We need more space to deal with the scheduler queues memory pools, and also the page tables. So it will take much time and energy. However, we want to remove the core as fast as possible. The general approach they follows just get state out of the way quickly or just dismantle it later or lazily. So how does it work in our OS in Barrelfish DC? First, close them away, and we are able to capture this OS node or all per core states, and we move it to a different core. Now, we add an OS scheduler into kernel that is able to dispatch different OS nodes. And we call that this core, and we call this case that one OS code to remove to a kernel that already have an OS node, temporarily parking OS node. And we can already notice that this approach is highly scalable as we only evolve 2 cores in process right now. We don't need to normally coordinate it into system. So what happens next? We can either move back to previous course or move it somewhere else. So what is OS node? And how do we capture this OS node? It's typically not clear in OS per core states. It's not explicitly defined and typically have many different data structure. So in this paper, we use partitioned capabilities systems to explicitly capture OS nodes, meaning entire per core states in a single data structure. I will introduce about the part of the partitioned capabilities. Capabilities are typed to reflect what the memory is used for. So a frame capabilities refers to memory that the holder can map into their address space, while a C note capabilities refers to memory that is used to store the bit representation of capabilities themselves. This captures all exciting information and memory allocation about applications. So all per core states in the kernel are now be accessed to the structure or reconstructed from the capability tree. We still need to be able to reach this and the structure and pass it around in our system. Therefore, we add KCB or kernel control block. KCB combines some states that don't need to persist across a kernel start. KCB is also a capability itself, means we now have a representable handle in systems to move entire per core state or out. So this method of state externalization and dynamic core booting is much more general mechanisms because we are now able to move the per core state around internally in our system, and we can also replace the kernel dynamically on needs of the OS. Also, I want to talk about interrupt and how can we deal with the interrupts. In general, interrupts they distinguish to 3 types of interrupting in system. First, handle local 2 cores and the CPU driver, like timers, and interprocessor interrupts which send between OS nodes, and also the device interrupts. So what happens if you have a device that runs on some cores and is migrate to different cores? Right now, we initially mask all interrupts on the core, and then we have to register the interrupts on device driver. So we typically doing this process is sometimes happening between and you have to go and check again if something happens into device, or you can pull the device while you are doing this shift. As the part of the evaluation section, we are going to show how it's exactly do this and how fast it is. So welcome to my partner.